Good morning, students. So, as a continuation of the previous class, today also we will learn something more about symmetry operations. So, we have already learned that symmetry operations are the actions that produces the same similar identical structure, indistinguishable structure. The symmetry operations can be axis, can be reflection, can be inversion, or can be rotation plus reflection. And the symmetry elements associated with them are expressed as Cn, reflections as sigma, inversion elements is I, and the rotation reflection is Sn. So today we are going to observe few of the interesting phenomena with these symmetry operations. Now, it has to be remembered that in a particular point group molecule, not necessarily always the symmetry operations commute. Commutation means xy equal to yx. Do not take as a simple arithmetic product. It is not a product of x and y. It only means that I am doing the Y operation first on the molecule followed by the X operation. The structure that we would be getting should be exactly the same if we do the X operation first on the molecule and then do the Y operation on the molecule. That is only possible if X and Y commute. If they do not commute, then their order actually matters. Then whether I'm doing the Y operation first followed by the X operation, or I'm doing the X operation first and then following the Y operation, this order will matter. If the order does not matter and always we are getting the same identical structure, then we must say that X and Y commute for this particular purpose. As for an example, let me take do C2 parallel to X. If you do a C2 parallel to X, that means the X coordinate won't be changing and the Y and the Z coordinate would be altering. So we are going to get, then you do C2 parallel to Y. So you are going to get minus x1, y1, and then z1. This is like C2 parallel to Z. That means, suppose this is my Y, this is my Z, my X is perpendicular to it. Now when I'm rotating the molecule 180 degree along the X axis, so the axis is actually coinciding the X axis. So y would be coming to minus y and your z would be coming to minus z, but your x coordinate is not going to be altered. So that is the reason the first one, the coordinate is showing as x1 minus y1 z1. Now if you do and c2 parallel to y axis, so that means the y coordinate is not going to be altered. The x1 is going to be minus x and the z1 is going to change its sign. So it would be again z1. The same, exactly the same result would be obtained if you do a C2 parallel to Z axis. Then the Z coordinates is not going to be changed, but the X and the Y coordinate is going to be changed. So we can say C2 along X and C2 along Y, they are producing a C2 along Z axis. So that means if you have in a molecule, if you have a C2 molecule along a x-axis and C2 molecule along a y-axis, then their product will automatically generate C2 along the z-axis. We know that if there are two group elements, then their product is also an element of the group. So that means the existence of the two symmetry element is ensuring the presence of another symmetry element. Let us take another example. This is about a C4 axis along Z axis and a sigma along XZ. Suppose so you are doing a sigma XZ on X1, Y1, Z1, any particular coordinate. Now, if you have a sigma plane along XZ axis, that would remain the X and the Z coordinate the same and the Y coordinate would be inverse. That means you are having a sigma plane which is containing the X and the Z is perpendicular to the plane of the board. So you are having a perpendicular plane which is containing X and Z. If you do a sigma operation or a mirror operation, that would invert the y coordinate. So that is going to produce you x1 minus y1 and z1. Now you do a C4 operation along Z. Now look here, if you do the C4, that is 90-degree rotation along the Z axis, your Y, whichever is your plus Y, would be actually the plus X, and whichever is your plus X would be altering and coming as minus Y. So whichever is your Y would be coming as plus Y plus x, and whichever is your x would be having your minus y. So your coordinate would be something like that. Now, is it not this similar that if you have a sigma plane, this is a sigma d plane, along this particular point, if you have a sigma plane, this is called sigma d plane. So whichever is your plus x is going to be your minus y, and whichever is your plus y is going to be minus y. So if you do a sigma d plane on this one, then whatever is your x coordinate, that is going to be your minus y, and whatever is your y coordinate is going to be minus x. Z is going to be unaltered. So this and this is the same. That means we can peacefully say that C4 along Z and a sigma XZ is actually equivalent to a sigma D plane. So presence of any two symmetry element is causing the third symmetry element to be generated. This is one example. This is the second example. Check whether C2Z and sigma xy, do they commute or not. For doing that one, let me work it on a particular coordinate x, y, z. If that is so, when I'm performing C2 along z, so that means again, this is my structure. Z is perpendicular to this. So I'm doing an 180-degree rotation. So my X would be minus X. I can write it as X bar. My Y would be minus Y. I can write it as Y bar. I can also write it as minus X minus Y Z. So now perform sigma XY on X, Y, Z. So that is going to alter your Z coordinate. So that is going to produce you X, Y, Z bar. So let me try it out. C2Z and sigma XY on X, Y, Z. So first that is going to give me X, Y, Z bar. And finally that is going to give me X bar, Y bar, Z bar. On the other hand, first let me do C2Z and then followed by XY on the same coordinate, that is going to give me C2Z. So X bar, Y bar, Z on the sigma XY is going to give me X bar, Y bar, Z bar. So I can say C2Z sigma xy, that is equal to sigma xy C2Z, because in both the times I'm going to get the same Cartesian coordinate. The transformation is the same Cartesian coordinates. The beauty is, can you say it that what is this? This is actually the result of an inversion center. An inversion center working on XYZ is going to produce me X bar, Y bar, Z bar. So I can say that if a molecule is having a C2 and a sigma perpendicular to the C2, that would ensure that the molecule is having another symmetry element, that is the inversion center. Now, with this one, we are here to find out another important definition, that is equivalent atoms and elements. Here, for BF3 molecule, BF3 is a planar molecule, and let me consider that the molecule is in the plane of the board. If that is the case, then the BF3 molecule is going to have a C3 axis which is perpendicular to the board. Not only that, the BF3 molecule would be having three perpendicular C2s. If you rotate the molecule along boron and fluorine, the axis passing through the boron and fluorine by 180 degree, this fluorine will come over here and this fluorine will go over there to give me the similar structure. So that means the boron, the BF3 molecule is going to have three perpendicular C2s. So I'm going to have one C3 and three perpendicular C2s. Of course, it is going to have three sigma V's as well. But the beauty is this C3, when I'm rotating the molecule along the, if the molecular plane is XY, and I'm having the Z axis is perpendicular to the board. So my C3 is along the Z. So when I'm rotating the BF3 molecule along the Z axis, that is along the C3 axis, which is along the Z axis, that time each fluorine molecule is going to be mixed up. And along that, the C21, the C21 would be converted to C22, would be converted to C23. That means all the C2 axis as well as all the sigma planes are going to be mixed with each other. So we can say, so if that is the case, that by a particular symmetry element, some other symmetry elements are going to be mixed with each other, then those symmetry elements are called equivalent elements. So the perpendicular C2s and the sigma V's are called the equivalent elements and the equivalent atoms. Here only, let me explain the definition of class. Class means that if there are two symmetry elements, actually I've written it wrong. It should be x inverse. X inverse AX. If there are two symmetry elements A and B, which is similarity transformed by another element X, this similarity transform means that they are following this mathematical expression x inverse AX equal to B, then we say that this A and B form a class. On the other hand, it is instead of doing following this particular mathematical expression, verifying it whether all the elements are forming this kind of mathematical expression or not, we can find out whether the elements are forming a class or not by the exactly the same way that we have done for the BF3. All the equivalent elements would be forming a class. So equivalent elements form class. It means all the equivalent elements are going to follow this similarity transformation. Let us come to some general relations among the symmetry elements and operations. General relations. Elements and the first relation says that the product of two proper rotation must be a proper rotation. As we have already seen that C2x and C2y is producing a C2z. That means the product of two proper rotation is producing another proper rotation. Then if there is one CN axis and then there is a plane which contains the CN axis, that means it is having one sigma V, then actually there should be n sigma V's. Just like that, like BF3, there is one C3 which is passing through the boron and which is perpendicular to the board. Now the sigma V's are these planes. So these particular planes contain the z-axis. So they are of course the sigma v. Now if you can find out that there is one sigma v, then there should be three sigma v's, because there is one CN axis and the sigma v is containing this particular CN axis. So actually there are three sigma v's. This is also a sigma v. This is also a sigma v. So there should be three sigma V's. The next relation says the product of two C2 rotation about axis that intersect at an angle theta is a rotation by 2 theta about an axis perpendicular to the plane of the C2 axis. So it says the product of 2 C2 rotation about axis that intersect an angle theta is a rotation by 2 theta about an axis perpendicular to the plane of the axis. Suppose there is a coordinate, a particular point x, y, and z. So you are doing C2x on it. So C2x on x, y, z. So obviously, if you are doing a C2x on this particular point, x coordinate is not going to be altered, y and z is going to be altered. So it is going to be x minus y minus z. Then you are doing another C2, which is C2y. So your x is going to be minus x, your y is going to be same, remain the same, your z is going to be altered. So you are having two C2 axes, C2x and C2y, which intersect at an angle 90 degree. So you are having theta equal to 90 degree. So that means you are going to have another C2 because 2 theta means 180 degree. So that is equivalent to another C2 axis perpendicular to the plane. So that means you are going to have C2Z. See, if you on the same plane, if you do C2Z, that is not going to alter your Z coordinates, but going to alter your X and Y coordinate and will make it minus X and minus Y. So that means if you are having C2X and C2Y, so their angle in between them is 90 degree. So you automatically that would generate another C2 axis, that is C2, and that should be along Z, which is perpendicular to the XY plane. The other one we have already seen that if we have a C2 axis and we have a sigma plane, that automatically generates the inversion point I. With this one, we have come to the almost to the end, and we can say, we can find out that which symmetry operations commute and not. So we can peacefully say that the following pairs of the symmetry operations, they commute with each other. Two rotations about the same axis. Two rotation about the same axis. Yesterday we discussed about benzene. So benzene is having a C6 axis and that is generating a C3 and a C2. So C3 and C6 going to commute with each other, whether you do the C3 operation first and then do the C6 operation, or you do the C2 operation or the C6 operation and then the reverse, the C6 operation and the C2 operation is not going to alter your structure. You are going to get the same structure. Reflection through planes perpendicular to each other. Reflection through planes perpendicular to each other. That means if you have a XZ plane and a YZ plane, so whether you are doing the reflection through the XZ plane first and the YZ plane later, or the vice versa, does not matter, is going to give you the same similar structure. The inversion and any reflection or rotation. So I into C2 is going to be C2 into I. Similarly, I into sigma is going to be sigma into I. Two C2 rotation about which are perpendicular to each other. Two C2 rotations which are perpendicular to each other. Rotation and reflection in a plane perpendicular to the rotation plane. So that means Cn and then sigma h is equal to be sigma h into Cn. With this one, we are coming to an end of this class. We are going to continue from here in the next class. Thank you.